Off the coast of Chiapas, southern Mexico, the tectonic machinery has broken its statistical protocol. 3 days after a magnitude 7.3 earthquake tore open the subduction margin of the Middle America Trench near the Mexico-Guatemala border, the physical response of the crust has diverged from standard geophysical decay models. Standard empirical laws dictated a rapid, predictable collapse in seismicity following the main shock. For the initial 24 hours, the system appeared to obey these classical parameters. A magnitude 6.0 aftershock hit roughly 30 minutes post-rupture, matching statistical predictions for the largest expected secondary event. A series of moderate magnitude 5 shocks followed through Friday night, including a magnitude 5.2 shortly after midnight. By Saturday morning, standard seismic evaluations formally classified the sequence as routine, anticipating 1 or 2 secondary magnitude 6 events at most before a systemic return to background levels. Then, the system ceased decaying and transitioned into an anomalous state of local energy release. Over a 9-hour window spanning Saturday evening into Sunday morning, at least 8 earthquakes at or above magnitude 4.5 clustered inside a restricted maritime corridor roughly 90 kilometers across. 3 of these events reached or exceeded magnitude 5.3. Most critically, the primary energy pulse of this cluster, a magnitude 5.7 earthquake, struck at 17:26 Universal Time, full 24 hours after the sequence had been officially designated as decaying. The footprint of this activity mapped out an expansive footprint spanning 32 kilometers north to south by 83 kilometers east to west, forming a flattened spatial distribution rather than a concentrated rupture zone. To comprehend the scale of this localized activation, consider the planetary baseline. Across the same observational interval, the entire global catalog of earthquakes at magnitude 4.5 and above rose from 137 to 144 events, a total increase of 7 moderate earthquakes worldwide. A single 90-kilometer segment of the Middle America Trench accounted for essentially the entirety of this global net increase. Across 40,000 kilometers of active plate boundaries, including the entire circum-Pacific belt and the mid-Atlantic ridge, global moderate seismicity condensed into one isolated box of ocean floor. This structural concentration exposes a critical observational fault line. The primary event in this burst, the magnitude 5.7 centered 72 kilometers southwest of Puerto Madero, highlights a profound instrumental discrepancy. The United States Geological Survey placed the hypocenter at a depth of 10 kilometers. Simultaneously, the European Mediterranean Seismological Center calculated the hypocenter at 29 kilometers. This is not a trivial rounding error. It represents a factor of nearly 3 on the primary vertical parameter of the event. Across the entire weekend burst, cataloged depths scatter across 10, 16, 18, 19.6, 29, and 35 kilometers, a vertical distribution spanning 25 kilometers of crustal section. In a subduction zone, where the Cocos plate slides beneath the North American plate at a rate of 76 to 88 millimeters per year, depth determines the underlying mechanics. A depth of 10 to 16 kilometers places the rupture on the locked interplate interface, where megathrust events accumulate stress. A depth of 29 to 35 kilometers places it deep inside the descending slab itself, driven by intraslab bending stresses. The current depth scatter indicates either severe observational limitation caused by one-sided onshore network geometry or the simultaneous activation of multiple distinct tectonic structures. Is this anomalous surge a vigorous, non-linear decay of a single interface rupture, or does the spatial scatter mask a fundamental shift in the mechanical state of the subduction zone? To determine which mechanism is driving this sequence, one must decode the structural architecture of the subduction zone itself. Off the coast of Chiapas, 2 separate seismic engines are stacked on top of each other. The primary engine is the interface, the contact zone where the descending Cocos plate locks against the overriding North American plate. This interface is the domain of megathrust ruptures, capable of generating magnitude 8 and 9 earthquakes and massive tsunamis. The secondary engine lies deeper within the descending slab itself, where the cold oceanic crust bends, pulls apart, and fractures under its own weight. Identifying whether these aftershocks reside on the interface or inside the slab is not an academic exercise. Interface sequences on a locked megathrust define the structural geometry in which foreshock sequences develop. Intra-slab events generally do not. The current depth discrepancy directly conceals which of these two engines is currently cycling. The origin of this data gap is a fundamental geometric limit of coastal seismic monitoring. Depth calculations rely on measuring the precise arrival time difference between direct seismic waves and waves that travel upward to reflect off the Earth's surface before reaching a station. When a network surrounds an epicenter, this timing provides pinpoint vertical precision. However, when an earthquake strikes 80 kilometers offshore, every recording station sits exclusively on one side of the rupture. This one-sided geometry degrades the mathematical convergence of the depth solution. Furthermore, when automated algorithms fail to resolve vertical location, seismic catalogs frequently default to a fixed placeholder depth of 10 kilometers. Many of the 10-kilometer entries in the Chiapas sequence are not measured realities, but computational defaults waiting for manual review by human seismologists. This ambiguity has fueled speculation that a larger rupture is imminent. However, rigorous systems analysis requires recognizing the physical limitations of foreshock identification. Statistically, foreshocks can only be identified in retrospect. Roughly 5 to 10% of moderate earthquakes are followed within days by a larger main shock, retroactively reclassifying them. Conversely, a major fraction of megathrust ruptures are preceded by foreshock activity. These twin realities make real-time classification operationally impossible. The 2011 magnitude 9.0 Tohoku earthquake in Japan was preceded 2 days prior by a magnitude 7.3 earthquake. At the time, that initial event was classified as a standard main shock with an ordinary aftershock sequence, the exact status assigned to the July 17th event off Chiapas. While modern instruments cannot distinguish a decaying aftershock series from a foreshock sequence, the physical system leaves a clear, testable threshold. The formal baseline assessment established that a transition to elevated major earthquake risk requires the appearance of multiple events at or above magnitude 6.0. As of the latest catalog updates, that specific boundary has not been breached. The ceiling of the weekend burst remains at magnitude 5.7, with the only magnitude 6.0 event occurring 30 minutes after the main shock on Friday, fitting standard statistical expectations for a magnitude 7.3 event. The regional crust, however, possesses a documented history of extreme energy release. In September 2017, a magnitude 8.2 earthquake struck the adjacent Tehuantepec region, the largest Mexican earthquake in a century. Mechanically, that event was an intra-slab normal faulting rupture at a depth of 70 kilometers, representing a complete tearing of the plate rather than an interface thrust. 7 earthquakes above magnitude 7.0 have occurred within 155 miles of this zone since 1950. The region is structurally prime for major ruptures. Yet while public attention remained locked on the Mexican Trench, secondary seismic activity suddenly materialized thousands of kilometers away. Within hours of the Chiapas burst, moderate earthquakes triggered along distant segments of the North American and Caribbean plate boundary, including a magnitude 5.1 south of Grand Cayman and magnitude 4.7 events off the Pacific coast of Nicaragua. This synchronous activity generated widespread assumptions that the Mexican rupture was actively pressurizing neighboring fault networks across the hemisphere. Applying the physical laws of stress transfer instantly deconstructs this narrative. Fault slip induces stress updates on adjacent structures through two distinct physical mechanisms: static stress transfer and dynamic triggering. Static stress transfer involves the permanent physical displacement of rock, permanently altering the stress field on nearby faults. However, this effect decays exponentially with distance, operating effectively only within 1 to 2 rupture lengths of the primary fault. For a magnitude 7.3 earthquake with a rupture length between 50 and 80 kilometers, static stress transfer is physically bounded to a radius of 100 to 200 kilometers. Grand Cayman sits roughly 2,000 kilometers from the Chiapas hypocenter, rendering direct static loading physically impossible. The second mechanism, dynamic triggering, operates via transient stress waves propagating through the Earth crust. While dynamic waves can destabilize distant faults, they act almost exclusively on structures already sitting at their critical failure threshold. The Nicaragua events, located 700 kilometers away along the same subduction interface, represent plausible candidates for weak dynamic interaction. The Grand Cayman event, situated 2,000 kilometers away on an entirely different transform system, represents a statistical baseline occurrence in a region that routinely produces moderate seismicity. Nevertheless, monitoring the North American-Caribbean boundary remains essential due to its own structural history. This boundary extends eastward from Guatemala through the Motagua and Polochic fault zones into the Cayman Trough and Swan Islands transform, a left lateral strike-slip system moving at 20 millimeters per year. In 1976, a magnitude 7.5 rupture on the Motagua Fault caused over 23,000 casualties. The Chiapas sequence sits directly near the triple junction where the Cocos, North American, and Caribbean plates intersect. This regional proximity raised questions regarding potential stress transfer to distant systems such as California. The mechanics governing this relationship are unambiguous. The same geometric scale limits that rule out static loading in the Caribbean apply to the California fault network at a distance of 2,500 kilometers. Dynamic stress waves from a magnitude 7.3 at that range are far too attenuated to trigger failure unless a target fault is already on the exact verge of rupture. Nothing occurring off Chiapas has altered the baseline probabilities for California. That reality is grounded in physics, not reassurance. Independently of events in Mexico, the southern San Andreas and San Jacinto fault systems sit at their highest measured stress states in a millennium, with the southern San Andreas accumulating strain uninterrupted since the magnitude 7.9 Fort Tejon event of 1857. The current crisis is defined not by hidden predictions, but by severe observational limits. No agency possesses a short-term forecasting methodology, and all database anomalies, such as orphaned tsunami logs, stem from automated system clearing protocols rather than suppressed data. The physical system now presents three specific, verifiable indicators: whether seismicity breaches the magnitude 6.0 threshold, how human-reviewed hypocenters resolve the depth ambiguity between the interface and the internal slab, and whether stress propagation continues along the Caribbean boundary. Until those parameters converge, the system remains locked between a productive aftershock sequence and an active multi-structure stress redistribution. Synthesizing the observational data, mechanical constraints, and structural parameters leaves two distinct, competing hypotheses for the ultimate trajectory of the Chiapas sequence. The first, and statistically most probable interpretation, is that a highly productive subduction interface has generated a vigorous but fundamentally finite aftershock sequence. Under this model, seismic decay is nonlinear and subject to temporary temporal clustering separated by quiet intervals. The weekend surge off Puerto Madero would simply represent the stochastic variance inherent to major subduction zones. However, the system has exhibited specific anomalies that prevent this case from being closed outright. The late arrival of the magnitude 5.7 primary peak, striking full 24 hours after the sequence was assessed as routine, violates smooth decay expectations. Furthermore, the overall rate of moderate energy release remains on the extreme upper bound of statistical modeling, while the depth scatter spans both the shallow interplate thrust interface and the deep, bending oceanic slab. This depth profile raises the secondary hypothesis. The magnitude 7.3 main shock may have induced a complex, multi-structure strain redistribution, simultaneously activating both the primary megathrust interface and internal fault systems within the descending Cocos plate. This region of the Middle America Trench has proven its capacity for extreme power, having produced the devastating intra-slab magnitude 8.2 Tehuantepec event in 2017, and at least 7 magnitude 7.0 or greater ruptures since 1950. Resolution between these two models will not come from speculative models or internet consensus, but from the hard metrics currently pending in the observational pipeline. 3 specific empirical indicators will dictate the physical outcome over the coming days. First is the strict magnitude 6.0 threshold. If secondary events cross this magnitude floor, the system transitions out of a standard aftershock decay sequence into an active strain transfer regime with elevated potential for a major secondary rupture. As of the latest catalog updates, the energy ceiling remains capped at magnitude 5.7. Second is the publication of human-reviewed seismic wave solutions. As seismologists manually review raw waveforms, the true hypocentral depths will condense, resolving whether the rupture patch is isolated to the shallow locked interface, contained within the deep descending plate, or actively fracturing both layers at once. Third is the spatial tracking of regional seismicity along the adjacent North American-Caribbean boundary. Continued moderate clustering near the Cayman Trough and Motagua fault system would indicate broader regional stress adjustments, whereas an immediate return to background levels will confirm those distant events were isolated coincidences. What the Chiapas sequence ultimately demonstrates is the precise boundary between observational instrumentation and the raw physical limits of predictive science. The data streams, public catalogs, and probability tables are operating with complete transparency, yet the underlying Earth system remains governed by nonlinear mechanics. The instruments have recorded the anomaly, outlined the physical constraints, and established the precise criteria for failure. The definitive measurement that settles the state of the subduction zone is being processed right now. As the observational data stream continues to update, the ultimate lesson of the Chiapas anomaly lies in understanding the strict boundaries of geophysical observation. The core tension of this sequence, a decaying aftershock series that suddenly spiked into a burst, accounting for virtually all global moderate seismicity, exposes the precise limits of real-time monitoring technology when deployed over offshore subduction zones. Human systems crave definitive, predictive conclusions, but physical subduction systems operate purely on stress budgets, frictional properties, and material strength limits. The inability of modern instrumentation to immediately deliver a single, unambiguous hypocentral depth for an event 80 kilometers out to sea is not a failure of intelligence or agency transparency. It is the raw geometry of a one-sided recording network sitting on the edge of a continent looking out over an ocean trench. When seismometers exist on only one side of a fault plane, wave arrival timing solution space widens, forcing automated algorithms into fallback default states like the recurring 10-kilometer placeholder depth. This technical constraint creates a temporary void of certainty, a gap where automated database artifacts, such as orphaned tsunami records, can be easily misconstrued as hidden warnings. In reality, every catalog feed cited across this sequence is public, unedited data, operating exactly as engineered. The deconstruction of this event reinforces a sobering truth about planetary mechanics. Nature does not provide clear, real-time warning labels distinguishing an unusually productive aftershock cluster from a true foreshock sequence prior to the main rupture. The physical properties of seismic waves emitted by a magnitude 5.7 aftershock in a decaying sequence are indistinguishable from those of a magnitude 5.7 foreshock preceding a megathrust event. Only in retrospect, after the crust has reached its ultimate strain limit and fractured completely, does the classification become clear. This was the exact operational reality facing Japan in 2011. When a magnitude 7.3 event preceded the magnitude 9.0 Tohoku megathrust by 48 hours. And it remains the operational reality off the coast of Mexico today. The science cannot bridge this gap with speculation. It can only establish hard, falsifiable parameters and track them against physical measurements. The single measurement that will settle what is occurring beneath the Middle America Trench, a unified, high-precision depth solution derived from manual human review of offshore ocean bottom and land-based seismic waveforms, will place the energy release squarely within the shallow, locked interface, inside the deep descending Cocos slab, or across both structures simultaneously. Until those reviewed parameters publish, the system remains in a documented state of elevated, clustered strain release along one of the most powerful subduction margins on Earth. The subduction machine beneath Chiapas continues its slow, relentless convergence at 76 to 88 millimeters per year, indifferent to human expectations of decay schedules or calendar norms. It operates entirely within the uncompromising, cold logic of structural mechanics, loading and unloading energy along planetary fault lines until the stress limits of the rock give way.